It's Dr. Guillaume Novelli. He's an assistant scientist at the University of Miami at the Erasmus, and he has a PhD in chemical engineering and environmental processes. And his research is focused on understanding how hydrocarbons are released at the bottom of the ocean and how they will rise and mix in the water column, and also how ocean currents, winds, and waves will transport these pollutants thousands of kilometers from the source to remote coastlines and sensitive areas. Dr. Novelli, are you on?
I'm on. Can you hear me? Good morning, everyone. Thanks for coming so early for a tech talk. Thank you, Monica, for inviting me and organizing these seminars. So, and thank you for the introduction. So yeah, I'm an assistant scientist at University of Miami. I've been working on oil modeling and oil studies for about 15 years now, and the talk today is about more or less the last 5 years of my research within the CART consortium. And so we review recent advances in drifters to study ocean currents and pollutant transport. So the consortium, CART, is a consortium of about 100 researchers from about 20 universities and research institutes in the US and around the world that is focused on physics, mostly ocean physics. And here you have a cartoon where you can see what all the different groups are studying. So some people study deep oil plumes and how the oil would rise and mix in the ocean and that get transported by deep ocean currents all around. And we also have groups working on atmosphere, specifically hurricane and storms, and how that affect the transport eventually of oil on the surface of the ocean and oil and gas. But I work more with the air and sea interaction people, specifically in observations, and we are trying to understand and measure and improve models on transport of oil from the deep ocean to the coast, and that includes all the interaction with wind and waves and rivers and whatnot. So every time there is an event like the Deepwater Horizon oil spill, the first questions everyone needs to know is where is the oil, where will it come from, where will it go, and how fast will it go there. And so our consortium is focusing on making tools that will help people monitor where is the oil, how to track it, and we also have people developing numerical models, so computations that will help you predict, knowing where it is at one point, it will predict where it will go, and we also make tools that evaluate these models, comparing the predictions to real observations so that we can improve these models and always give better forecasts. So what you see in these images are some images from the press of Deepwater Horizon, and I would just like to draw your attention that it's all surface oil because that's what you can see and that's what you can act on. And what you see is mostly ocean and limited places where the oil accumulates in small ribbons, small lines. And so one of the difficulties is to find it when there is bad weather, keep track of it at night. And so that's the problem of monitoring. How do you track it under all kinds of conditions? How do you find it? And so from an oceanographer point of view, for us, determining where it will be, it's the same as finding out what are the currents. So if I want to know where it's going to be tomorrow, I need to know where it is today, and I have to know the currents that will transport it from one place to another. So for us, the big question is how to measure ocean surface current over a large domain eventually, like the size of the Gulf of Mexico, for example, and relatively frequently, so that your data is really almost real time. That would be the best case scenario. And so there are lots of technology around. You can use satellites if you want to get a large domain coverage, but then usually you lose the frequency because satellites overpass are once a day, once a week, depending on the satellite. And other technology like radars or acoustic measurements on buoys, but usually you get a very good frequency, it's very accurate, but usually you have a small domain, so only where your instrument is you can measure. So right now the technology that is most practical to measure currents everywhere frequently and accurately is ocean surface drifting buoys, which we refer to as drifters in general. So here you have pictures of the two standard oceanographic drifters. On the left, the cod drifter that was developed by Davis at Scripps in the early 80s. And on the right, you have the NOAA drifter called SVP drifter, and that was developed in the 90s. At Scripps also, essentially. And so what's a drifter? A drifter floats first, and it has a buoy. So on the right, you have this spherical buoy here that's about 1 foot in diameter. On the cod drifters have 4 little buoys at the end of these arms. And why do we have a buoy? Because inside the buoy, we have electronics that transmit information, data to satellites. So we need a view to the sky. And so this buoy usually carries lots of batteries and electronics that gather the data from the sensors. And this data can be as simple as only position, like GPS data. But you can also have sea surface temperature, atmospheric pressure, salinity. And the second very important component of the drifter is what we call a drog. So on the right, you see it has the shape of a very long sock. And on the left, it's more like a sail, like a cross sail, and the idea is to anchor your drifter in a current at a given depth. So the cod drifter is about 1 meter tall, so it averages the surface current in the upper meter, and the NOAA drifters try to target a depth of 15 meters, 15 meter deep. So those are standard, very accurate, very well calibrated drifters, but if you want to study oil spill, the problem, as you can see, first is their size, because this one follows the current at 15 meters deep, and that, as we said before, we are more interested in what's at the surface, and the oil at the surface is typically between 1 micron and maybe 10 centimeter depth, where it accumulates and where it's more toxic. And so both of these options are a little bit too big to study oil spill. So what about oil drifters? Of course, since oil spills have happened, there have been a lot of research on trying to make an oil drifter. And so here you have a few examples from publication from the 90s. and on the left you have what's called the Orion buoy, and you can see the hand of the operator here, so it gives you an idea of the size of it. So how did they try to develop these drifters? What they did, they create oil spills. They just dumped a few barrels of oil in the ocean and drop all their different kinds of drifters in the oil and stay with it, with the ship, for a few hours, for a few days, and then try to select the design that would stay with the oil. And the idea is, if I have a drifter that moves like oil, I can drop a lot of drifters instead of dropping oil to try to understand and improve my models. And what they found out is that when there is low wind, anything that's small, like this Orion buoy or this local drifter or even this sphere here on the right, anything that's small has follow the oil very well as long as there is no wind or little wind. And that's less than 7 meters per second wind, less than 10 knots, something like that. As soon as there is a lot of wind, nothing really follows the oil, or because we cannot track the oil, it gets mixed by the waves and it goes underwater and reappears somewhere else. And of course, these drifters cannot follow the oil as soon as it as it is entrained underwater. So that's the first thing. And here are a few other drifters that have been used recently in different oil spills. So on the left, these devices have been used during the Prestige oil spill. Maybe you've heard about it. It's one of the last biggest accident in Europe off the coast of Spain. And here you have this small satellite beacon. So you cannot see the size there, but it's about a foot tall, the red part, and that's basically batteries in red. The yellow is a piece of foam to make it float, and then it has an antenna to drop its position. So how it works is an airplane fly over the ocean. When they see oil, they drop it through the window, and then it reports its position, and then this position is used on land by the scientists to as an initial position for the oil in their model, and from there they add the current that they compute, and they say, okay, so tomorrow maybe it will be this place or that place. Here is another one. As you see, they have tinkered a bit, and they have mixed the SVT surface buoy, and they use the transmission capability, and they mix it with the cod to try to anchor it in the water a little bit better and to track the surface. And here on the right, there is the Far Horizon Drifter. So that's a smart design, very practical, because it's made to be dropped by airplane. So with an airplane, you can cover a lot of ground very fast. So you can drop lots of drifter very far and in many places. And the parachute, once the drifter falls in the water, is used as a drag or as a sea anchor. But I would draw your attention to the fact that if you look at all these different drifters, they all have different shapes, different weights, different sizes, and none of them has been thoroughly tested and calibrated. It's more, they are useful usually for a few hours, because you can assume that for a few hours, for a day maybe, their drift will not be too different from the oil, and so you can use this buoy from one day to another to find the oil the next day. You go to the position it gives you, and then that's fine. But you cannot use them for more than a few days, because they will not drift like a centimeter thick oil slick. And so for us, that's for our goal of measuring current at high frequency over a large domain and close to the surface. We found out after deploying hundreds of drifters that we needed to deploy like 1,000 at a time, so that it would be useful. And then that created new problems, new constraints. And here's the list of these constraints. If you are going to deploy 1,000 drifters, let's say 5 kilo drifters, that means 5 tons of material you will dump in the ocean, and most probably you will not get it back, because how do you find 1,000 drifters a month after dropping them in the ocean? Even if you know their position, they are going to be spread all over the Gulf of Mexico, and it's going to cost much more to capture them. So it's very important that they are harmless for the environment. So a very important point for us was to create something that is biodegradable. Also, when it comes with handling a large number of instruments, so typically a drifter experiment is made with 5 to 10 drifters, and we are talking about 1,000. So what you need is something very easy to operate, very safe to operate, and very easy to handle, because when you repeat the motion 1,000 times, you can make mistakes, you can get injured, fatigue. So something very easy. We need something very small so that we can carry it on the ship. We did an experiment in 2012 with 300 code drifters, and we could only fit 50 at a time on the deck of the ship. So that gives you an idea of, okay, 1,000, how are you going to do that, right? You only need 10 boats, 20 boats to do that. And also you need to be able to manufacture them. So you can make a drifter in your garage by yourself if you have 2 days to spare. But if you want to make 1,000 of them, well, you need to go to an industrial production technique. And of course, if you want to do science, well, you need something that's reliable, that's going to withstand the ocean conditions, something that's accurate, but most importantly, something that's calibrated so that you know its behavior. And so that's what our group set up to do. We're trying to make the new car drifter, and so here's some rendering of a few of the designs that we've tried over the years. It took us a bit over almost 3 years to reach a final product, and so we started with an idea of doing it out of wood with 3 interlocking pieces, and you would build it a little bit like Legos. So you would clip it into each other, and so that's the simple, that would occupy space when it's not mounted, and you would have a surface disc that would act as a float, and then, like the code, a drog, a sail made of wood panels. And we went ahead, built the first prototype, and then what we do is we test it in the lab under different winds and waves, and then we find, okay, that's too big, that's too small. What we found, for example, with this first one is that when you put it and you have a little bit of wind, it creates short waves, and when you have short waves, then your drifter, instead of going straight, is going, if the waves are going this way, then your drifter is inclined. And then if the water is here, the wind would catch it here, and then it will move around, pushed by the wind like a sailboat. And so we started removing material at the surface so that the wind would go through and the drifter would stay straight. And we removed more material so that breaking waves wouldn't push it more. And then we started having problems with waves. We solved the wind, and then we had problem with waves. The drifter would oscillate and accelerate and move much faster than the current. So we tried to add at the bottom, I don't know if you can see, but like a flat piece of steel plate at the bottom to try to damp the oscillation caused by the waves vertically. And then we increased, and then we increased the surface area at the bottom to try to solve that, and it was still a problem until we decoupled the surface float from the drog just by putting a piece of chain in the middle, and then, like magic, it stopped all the problems of the wave. Then, so we do all this test in the lab. We make a prototype, go to the lab, test it, find a problem, try to fix it, make a new prototype, test it again, go back. It works, okay, let's bring it to C. We bring to the C, we make some tests, new problems, new solutions, and the last problem was actually the wood. When you put wood untreated in the water, it absorbs water. And so after 15 days, for example, for this design, after 15 days it sinks. And so that was, once we had the design correct, we had to find the right material. And so the right material for us is the PHA. So this PHA resin, and that's created by these bacteria that you see here, and you feed them with sugar, in our case corn sugar, and they accumulate in their body these white blobs. So this is a polymer derived from the corn sugar, and then you can extract this polymer, and it has the same properties than the usual petroleum-based plastic. And so it is used currently to make beach toys, it's used in agriculture, any kind of plastic that would be abandoned in the soil or in the sea, and so it just degrades, it becomes food again for the bacteria when they run out of food. And so the big advantage is that we can process it like usual plastic, so we can create a mold, like they make molds to make chairs or plastic utensils, and then we can crank up the production and generate this design. So that that's our drifter.
Here.
So you can see the floats here. It's like a donut, and it has a very aerodynamic profile. So it usually sits under the crest of the waves, and so the wind doesn't push it too much. This is what goes inside the enclosure. So there's a battery pack and a GPS from Global Star. And this is how it works. So this is after 1 hour of work, opening these crates and starting assembling. 2 people. We assembled 100 of them. As you can see, the drone can stack onto each other. They're very practical to use on the boat. And here we have laid down all the floats and start all the GPS with a magnet that we put in front of it. It starts them, and we're just checking that they are transmitting before we put them in the water. So we have done a lot of calibration in the Sustain Lab at the University of Miami. So basically we generate different waves, different winds, and we check in the lab that we can, that the drifter and the design follow the current like it should. So I will not go into the details of this graph for time reasons. So we tested in the ocean as well. So here you can see a picture where we compared the code drifter, our design, the last wood design, and a sphere. And on the right, those are the trajectories, 15 minutes trajectories. So all the drifters will drop together at that point. And after 15 minutes, you can see they have a very different behavior. And that's because they react differently to wind, waves, and currents. The sphere in particular is much faster than the current, like 6 to 7 times faster than the surface current. The wood version here is about 50% faster than our drifters, which is in good agreement with what we measured in the lab. And here, the green and blue are the code drifters, so the standard one with the new one. and you see they stay together.
Sorry,
And,
please use your phone
here,
if you're not the presenter. Please mute your phone. Thank you.
thank you. I have just like 1 minute. We made here a number test in the girlfriend, and we checked that the code and the car drifter stay together for more than 1,000 miles over a week. We also developed a biodegradable parachute and release system that we tested from a helicopter, so that's practical from an operational point of view for air deployment. And here basically just a few results. So we've deployed 1,000 in the Gulf of Mexico in 2016, and those are the trajectories, about 2 month trajectories, the gray lines, and the red points are the last position after these 2 months. They are all released on these 3 yellow dots. As you can see, we can cover very rapidly the whole Gulf of Mexico. It has been used by other people in other places since then. So it has been used in the Arctic Ocean. As you know, the Arctic is warming up much faster than the rest, and the ice is disappearing. So we have a new ocean created there. And we dropped a few drifters there, 20 drifters. And Laura Bracken, also in Miami, here led a citizen science experiment. So it's very easy to use. And we've studied the residence time of pollution inside the bay, and this is a very shallow bay. It's often 3 to 6 feet deep, so you cannot use most of the conventional drifters to do that, but our drifter can go through. We also made a lot of work to compare it to oil, and we found out that the drifter without drag moves very much like thick oil. For example, here on the bottom map, what is what you can recognize, I'm sure, the Mississippi Delta and a little bit of the coast around it. So what is in red is where oil was found on the shore during the assessment post Deepwater Horizon, and what is in green and blue is where our drifters without drag have landed. And one of the things we see is everywhere there is a green point, there is also a red point. So the drifters mimic very well the oil when they are next to the shore. And so that's work I'm finishing now, and that will be submitted for publication soon. Just a summary. We developed a new drifter that's biodegradable and calibrated, and that has been used a lot already, and it's available to the community. And yeah, I just want to thank Gomri and CART for their support over the years, and you for listening until now. Thank you very much.
Thank you. Do we have any questions in the room? We're going to go ahead and ask questions to Dr. Novelli because he's going to have to leave, so he won't be on the line when we do our question and answer. So if anybody has a question, I will go ahead and repeat it into the phone, and he can answer it. Yes. What exactly is your drifter called?
Usually we say the CART drifter from the consortium.
Mm-hmm. So they named it after the consortium.
Yes.
Any other questions? That is all. If we get any other questions, Dr. Novelli, we will go ahead and forward them to you, and I can always send them out to the folks in the room and to people online with your answers to their questions. Thank you so much for joining us.
Thank you for having me.
We appreciate your willingness to present via webinar, even with our technology issues. Thanks again.
No problem. Thank you very much.